Hello! In the previous lecture, we reviewed 4 techniques for searching for a number in an array. Linear search, where we sequentially check every position of the array. Binary search, where we discard portions of the array to refine the search. Direct addressing, where we use a bit vector to check for the presence of a number. And hash tables, where we use a hash function to determine the position of the number being searched for in the hash table. We also saw that using a hash table is the best option, as it is as fast as direct addressing, but without requiring as much memory. In the example we studied in the last lecture, we saw how each number was mapped to a different position in the hash table and how fast it was to search for them after doing that mapping. So, the mapping part of the process was fundamental for the good performance of the hash table when searching for a number. However, the mapping was performed with us knowing beforehand how many and what numbers could be stored in the hash table. Now, let's look at what problems arise when that is not the case. Let's assume we are using the same 7-element hash table as before and the same hash function. But we do not know how many or what numbers are going to be stored in it. Let's assume that the numbers to store in the hash table are 21, 3, 14, 5, and 10. So, we store number 21 in position 0 of the hash table. Next, number 3 goes to position 3. And now we have a problem with number 14. Number 14 should be stored in position 0, but position 0 is already used by number 21. This situation, where 2 numbers are hashed to the same position, is known as a collision. In this case, numbers 21 and 14 have collided in position 0. When we do not know the numbers to be stored beforehand, and this is the most common situation, collisions are inevitable. Given that collisions cannot be avoided, how can we deal with them? In this lecture, we will look at 3 collision resolution methods. The first method is known as extend and rehash, and it consists of 3 steps. Firstly, we must enlarge the hash table, which corresponds to the extend part of the method's name. Let's look again at the example where number 14 collided with number 21. First, we need to create a new hash table that is, for example, double the size of the original one as shown here. After we have done that, we can proceed to the second step. In the second step, we need to modify one part of the hash function. If a hash table has m positions or buckets, the hash function usually ends with the operation modulus m to make sure that every number goes to a valid bucket. In the original hash table of our example, the hash function ended with modulus 7 to make sure every number would be in the range of 0 to 6. This part of the hash function is known as the reduction function of the hash function, because this part is in charge of reducing the resulting number to the range of values valid as positions in the hash table. If we increase the number of buckets, then we need to update the reduction function. In this example, the reduction function must be updated to modulus 14, because the new hash table has 14 elements. After enlarging the hash table and updating the reduction function accordingly, we can proceed to step 3. Finally, the third step consists of making the content of the new hash table consistent with its new hash function. To do so, we need to rehash the numbers that were already stored in it. This corresponds to the rehash part of the method's name. So, we rehash number 21 to find its correct place in the new hash table, that is, bucket number 7. And we also rehash number 3, which goes to bucket number 3. Now that all numbers already stored have been rehashed, we can discard the previous hash table and continue storing the remaining numbers in the large hash table, 14, 5, and 10. So, after applying the new hash function to the numbers 14, 5, and 10, we find out that they are stored in positions 0, 5, and 10. This collision resolution method can be applied in two ways. The reactive way is the one we just used. Immediately after a collision occurs, we extend and rehash. Or we can do it in a proactive way. That is, every time a given number of buckets is used, we extend and rehash. Because determining the minimum number of buckets to extend and rehash is not practical, hash tables of different sizes will have different minimum values, we refer to the load factor rather than the number of used buckets. The load factor is the fraction of buckets used. So, the proactive way of dealing with collisions uses extend and rehash every time the load factor exceeds a given threshold. That was for extend and rehash. Now, let's move on to the next collision resolution method, linear probing. This method searches for the next available bucket to store the number in collision. Let's go back to our example, where number 14 is colliding with number 21 in bucket 0 of the hash table. If linear probing is used as a collision resolution method, then the next bucket in the hash table is probed. If it's available, the colliding number is stored there. In this case, number 14 is stored in bucket 1, and we can proceed to store the rest of the numbers. Number 5 goes to position 5, and number 10 would go to bucket 3. But number 3 is already in bucket 3, so there is another collision. Using linear probing, the next bucket is examined. Bucket 4 is available, and so number 10 is stored there. And now we move to the third collision resolution method. This method is called separate chaining, and what it does is create a chain of buckets at every position of the hash table. At the beginning, the chain of buckets at every position is empty. That is represented by arrows pointing to null. And then, as numbers are stored in the hash table, they occupy their original bucket at different positions of the chain. In this slide, we can see how numbers 21 and 14 that are hashed to bucket 0 are stored in the chain of bucket 0. The same is the case with numbers 3 and 10, which were both hashed to bucket 3. The advantage of using chains is that they can grow and shrink on demand, as numbers are inserted and deleted from the hash table. We will see how to implement separate chaining when we study linked lists in future modules. Now, let's talk a bit about complexity. The best case for the operation of a hash table happens when there are no collisions at all. In that case, inserting a number in the hash table takes a constant time. That is, the time complexity of inserting a number is θ1. The same happens with search. If there are no collisions at all, we just need to check whether or not the corresponding bucket stores the number being searched for. This takes constant time, and so it's also θ1. Finally, if we need to remove a number from the hash table, we simply check its position by applying the hash function. If the number is there, we delete it by storing a number -1 in that position. The performance in the worst case depends on the method of collision resolution used. Let's quickly analyze the case of separate chaining. The worst case occurs when everything collides, that is, when all numbers hash to the same bucket. In that case, only insert is theta1 if you insert at the start of the linked list. If you have to search for a number, you must go through the entire list in the worst case. If the list has n numbers, doing that will take n operations. Therefore, search is theta n. Finally, if you have to delete a number, you first have to search for it. That is why delete is also theta n. With this, we finish our study of hashing as a fast technique for searching. Please calculate the time complexity of the other two collision resolution techniques and check your answer against the solution document when you are ready.